In the previous chapter, we looked at chemical equilibria. We're now going to apply those same principles to aqueous solutions of acid and bases. Perhaps the first time that some of you guys have seen this in chemistry. Acetic acid in vinegar, citric acid in lemons, magnesium hydroxide in commercial antacids, and ammonia in household cleaning products are some of the basic acids and bases that we encounter in everyday life. The characteristic properties of acids and bases have been known for centuries. Acids react with metals such as iron and zinc to yield hydrogen gas, and they change the color of litmus paper from blue to red. Bases feel slippery, and they change the litmus from red to blue. Let's look at some very general acid-base concepts. We usually define acids as anything that dissociates in water to produce a proton, a hydrogen ion, or a base as anything that dissociates in water to produce hydroxide ions. But the Arrhenius theory doesn't account for certain compounds like ammonia, NH3, that doesn't contain hydroxide groups. In 1923, a more general theory of acids and bases was proposed independently by Danish chemist Johann Bronsted and the English chemist Thomas Lowry. According to the Bronsted-Lowry theory, an acid is any substance that can transfer a proton to another substance, and a base is any substance that can accept that proton. In short, acids are proton donors and bases are proton acceptors, and between both is a proton transfer reaction. To see what's going on in an acid-base reaction, keep your eye on the proton. For example, when a Bronsted-Lowry acid, described here as HA, dissolves in water, it reacts reversibly with water in an acid dissociation equilibrium. The acid transfers a proton to the solvent, which acts as a base, or a proton acceptor. The products are the trigonal pyramidal hydronium ion, H3O+, which is the conjugate acid of water, and A-, which is the conjugate base of HA. The easiest way to look at this is the conjugate base of an acid just requires you to remove a proton, and the conjugate acid of a base has you adding that proton to it. Again, the conjugate acid here of ammonia is just adding a proton to give you NH4+, and the conjugate base of water is just removing a proton. Remember that water can act as either an acid or a base, in which case it's called amphiprotic. Remember that a strong acid will dissociate 100% in solution, whereas a weak acid would not. With equal concentrations of reactants and products, what do you suppose will be the direction of this reaction? As we stated earlier, a strong acid is an electrolyte, and it dissociates 100%. But weak acids and very weak acids undergo partial dissociation. Only a small fraction of the weak acid molecules transfer a proton to water, and the solution therefore contains mainly undissociated HA molecules along with small amounts of the hydronium ion and the conjugate base A-. Here's a table that shows the relative strengths of acids and bases. Be sure to memorize the strong acids and the strong bases. Why is one acid stronger than another? It has to do with the strength and polarity of the bond. In general, the weaker and more polar the bond, the stronger the acid. So acid strength increases as you go down a periodic table, but acid strength increases as you go from left to right. The strengths of binary acids of the second row elements, for example, increases as the electronegativity of A increases. In this case, the carbon-hydrogen bond is relatively nonpolar, and methane has no tendency to dissociate in water into the hydronium ion and into the CH3- ion. Oxyacids are those formulas that contain an oxygen. Two factors are going to determine what the acid strength is. For oxyacids that contain the same number of hydroxyl groups and the same number of oxygen atoms, acid strength increases as the electronegativity of Y increases. For example, the acid strength of the hypohalous acid HOY, where Y is any sort of halogen, increases as the electronegativity of the halogen increases. A second factor is that for oxyacids is that acid strength is going to increase as the oxidation number of Y increases, or as the number of oxygen increases. So in the last section, we saw that water can act either as a proton donor, as an acid, or a proton acceptor. In the presence of an acid, water behaves as a base, whereas in the presence of a base, water behaves as an acid. It's not surprising, therefore, that in pure water, one water molecule can donate a proton to another water molecule in a reaction in which water acts as both acid and base within the same reaction. Called the dissociation of water, this reaction is characterized by the equilibrium equation Kw is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion. As discussed earlier, the concentration of water is omitted from the equilibrium constant because water is a pure liquid. At 25 degrees, the concentration of both the hydronium ion and the hydroxide ion is equal to 1 times 10 to the minus 7 molar. The ion dissociation constant is Kw, which is equal to 1 times 10 to the minus 14, which is at the very root of the pH scale. One can calculate either the hydroxyl concentration or the hydronium concentration by knowing one or the other. If the hydronium concentration is high, you have an acid. If the hydroxide concentration is high, you have a base. And where they're equal, of course, it's neutral. The pH scale runs from 0 to 14. The pOH scale is the inverse of that scale. They're both equal to negative logarithm of the hydronium concentration for pH or negative logarithm of the hydroxide ion concentration for pOH. Here are some various substances and where they fall on the pH scale. Remember, there are no units for pH. There's a special rule for calculating the number of significant figures in pH, and that is first calculate the number of significant figures that you have in the hydronium ion concentration, and then go out to that many decimal place. So in this example, you have 2 significant figures, so your answer has to be expressed to 2 decimal places after the decimal point. Here's a very straightforward example of a calculation with pH. Be sure that you do this with your own calculator. Be familiar with where the log button is, as well as the inverse log. Measuring pH usually involves some sort of acid-base indicator, as shown here in this reaction. Here are the common indicators that you might see in lab. Bromothymol blue changes color in the pH range of 6 to 7.6, from yellow in its acid form to blue in its base form. Again, calculating the pH of an acid, a strong acid or a strong base, is fairly straightforward. Here we have a strong acid, nitric acid, which involves simply the definition of pH, which is negative logarithm of the hydronium ion concentration. Be sure to use the right number of decimal figures after the decimal point. Likewise, you can calculate the pH of a strong base solution by calculating the hydroxide ion concentration, then calculating the hydronium ion concentration, and then plugging it into the pH equation. But for a weak acid and a weak base, something else happens. Because you cannot assume that there's 100% dissociation between the hydronium ion and A-, then you must be given an acid dissociation constant, which we label as Ka. Values of Ka and pKa are listed in this table as they would be given to you in a problem. Just as the pH is defined as negative logarithm of the hydrogen ion concentration, so the pKa of an acid is defined as negative logarithm of the Ka. Note that the pKa decreases as the Ka increases. As indicated by the equilibrium equation, the larger the value of Ka, the stronger is the acid. If you're ever needing the Ka values of a weak acid, you can also look at Appendix C in the book. So your first step to calculating what the Ka or the pKa is for hydrofluoric acid, a weak acid, is to determine what the hydronium ion concentration is going to be. In that case, it's necessary to make an ice table. Once the hydronium ion concentration is calculated, then you can also deduce from that what the F- concentration is, as well as the hydrogen fluoride concentration. Plugging into your values of product over reactant, you get the Ka, and plugging into a negative logarithm of the Ka, you can get the pKa. See if you can do this weak acid. Hydrocyanic acid, or hydrogen cyanide, since it's a solution. You want to calculate the pH. Again, your first focus should be on calculating the hydronium ion concentration. You do that through using the Ka that is given in the problem. Once the hydrogen ion concentration or the hydronium ion concentration is calculated, simply plug in so that you can solve for the pH. You'll notice here, because X is a very small number, because it's a weak acid and dissociates very little, we eliminate it in the denominator. The key points here in calculating the pH of a weak acid or a weak base is to make sure that you have a balanced equation. The second thing is to make an ice table, and then substitute the equilibrium concentrations into the equilibrium equation for the principal reaction and solve for X. Then plug it into your pH formula. A common question is, How do you know if you can cancel out the x in the denominator or not? One way of knowing it is basically x can be neglected if the value of the initial concentration doesn't change when x is subtracted from it. In the previous example we saw, x could be neglected because it was greater than or equal to 0.01. It's important to check the validity of the simplifying approximation in every problem because x is not always negligible compared to the initial concentration of the acid. In addition to Ka, another useful measure of the strength of a weak acid is what's called the percent dissociation, defined as a concentration of the acid that dissociates divided by the initial concentration of the acid times 100%. Acids that contain more than one dissociable proton are called polyprotic acids. Polyprotic acids dissociate in a stepwise manner, and each dissociation step is characterized by its own acid dissociation constant, Ka1, Ka2, and so forth. For example, carbonic acid, which you see here, the diprotic acid that forms when gaseous carbon dioxide dissolves in water, is important in maintaining a constant pH in human blood. Here's the dissociating reaction associated with that. You'll notice that Ka1 is usually greater than Ka2, and if there's more, then Ka3 would be even lower. Because of electrostatic forces, it's more difficult to remove a positively charged proton from a negative ion, such as HCO3- than from an uncharged molecule, such as H2CO3. So Ka2 is less than Ka1. In the case of a triprotic acid, like phosphoric acid, it's more difficult to remove hydrogen ion from an anion with a double negative charge than from an anion with a single negative charge. So Ka3 would be less than Ka2. So again, because of electrostatic forces, it's more difficult to remove a positively charged proton from a negative ion than from an uncharged molecule. So Ka2 is always going to be smaller than Ka1. The first step to calculating the pH of a carbonic acid solution is by making an ice table. Substituting the equilibrium concentration into the equilibrium equation for the principal reaction would give you the next slide. Once X is obtained, where you know what the hydronium ion concentration is, you simply plug it in to get the pH. Weak bases such as ammonia accept a proton from water to give the conjugate acid of the base and the hydroxide ions, as shown here. The equilibrium reaction of any base with water is characterized by an equilibrium equation, just like what you saw for the dissociation of a weak acid. Here are the base protonation constant or base dissociation constant, Kb, in relation to some common bases. Be sure on a test not to confuse the Ka value and the Kb value. Calculating the pH of a weak base is done in the same manner that we just solved the problems for a weak acid. The first thing to do is to make an ice table. Then the value of X is obtained from the equilibrium equation. When you subtract the value of X from the initial concentration, we see that x in the denominator is negligible and can be canceled out. When Ka is given for a base, it is often derived from the formula listed below, where Ka times Kb is equal to Kw. Again, be sure not to confuse values of Ka and Kb in a problem. Another way to look at that is that the pKa plus the pKb is going to equal 14. In a common neutralization reaction, when an acid neutralizes a base, the salt is formed. Salt solutions can be neutral, acidic, or basic, depending on the acid-base properties of the constituent cations and anions. As a general rule, salts formed by the reaction of a strong acid with a strong base will give a neutral solution. Salts formed from the reaction of a strong acid with a weak base will give an acidic solution, and salts formed by the reaction of a weak acid with a strong base will give a basic solution. It really depends on which one dominates in the solution. The following cations from strong bases and anions from strong acids will yield a neutral solution. Ammonium chloride, which is derived from a weak acid, and hydrogen chloride will yield an acidic solution. Hydrated cations of small charged metal ions, such as Al3+, will also yield an acidic solution. In general, the acidity of a hydrated main group cation increases from left to right in the periodic table as the metal ion charge increases and the metal ion size decreases. Salts such as sodium cyanide that are derived from a strong base and a weak acid yield basic solutions. In this case, the cation is neither an acid nor a base, but the anion is a weak base. So what happens when the salt contains acidic cations as well as basic anions? Well, in this case, you need to look at the Ka value and the Kb value. If Ka is greater than Kb, the solution will have an excess of hydronium ions, which means the pH will be less than 7. If Ka is less than Kb, then the solution will contain an excess of hydroxide ions. And if K is about the same as Kb, then the solution should be neutral. So let's look at the Ka for the ammonium ion and the Kb for the carbonate ion and see whether Ka is less than or greater to Kb. Because Kb is greater than Ka, the solution is basic. Here's a summary of the acid-base properties of the salts. We will be practicing these in class. In 1923, the same year in which Bronson and Lowry defined acids and bases in terms of their proton donor and acceptor properties, the American chemist Lewis proposed an even more general concept of acids and bases. He noticed that when a base accepts a proton, it does so by sharing a lone pair of electrons with the proton to form a new covalent bond. Using ammonia as an example, the reaction can be written in the following format, in which the curved arrow represents the donation of the nitrogen lone pair to form a bond with the hydrogen ion. In this reaction, the proton, the hydrogen ion, behaves as an electron pair acceptor, and the ammonia molecule behaves as an electron pair donor. Consequently, the Lewis definition of acids and bases states that a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. The reaction of copper plus 2 ion with ammonia is a Lewis acid-base reaction in which each of the 4 ammonia molecules donates a pair of electrons to Cu2+ to form a deep blue color. Another example of neutral Lewis acids with oxides of nonmetals, such as, in this case, SO3, happens when SO3 reacts with water. This can be viewed as a Lewis acid-base reaction in which the sulfur trioxide accepts a share in a lone pair of electrons from a water molecule. Be sure to practice these problems and study the lecture guide so that you will be prepared for test number 3.